Hi, I'm Liwei Chen from National Jiao Tong University, and this work is in cooperation with Robin Chen from National Taiwan University. And the first author is Liao. Unfortunately, he's not able to attend the UIST. So on behalf of him, I will be presenting DualPlus. So let me show you a quick videos demonstrating the basic idea of DualPlus. It is a method that boosts the effectiveness of traditional drill by active haptic ticks. So when the user's drill touches a button here in app groups, the haptic ticks prompts the switches of modes through the user's skin sensations. To select an app, he releases the touch until the app of selection is haptically prompted. The speed of previous video was actually tuned down a little bit for you to catch the ideas. Now let's have a look at the real speed. As you can see, the original haptic ticks comes with high frequencies. And even under this speed, the user can still manage it to select correctly. So the main contribution of this work not only lies in the concept we introduced, but also two effective DualPlus designs derived from our user studies, which I will go through later. Because the mechanism of DualPlus requires only touch input and vibration output, it is easy to apply to a wide range of applications, such as typing on smartwatches with several keypads, enabling single-handed typing on smartphones, unlocking devices by counting vibrations secretly, and augmenting stylus-based interactions. So far, I have introduced the basic ideas of DualPlus, and here I will go through the motivations. Dual, also known as the long press and touch, or touch and hold, is one of the most common mode switching methods. And for a long time, it has been used in stylus input for switching mode and activating hidden menus. Dual is easy to use and understand, and we still often find it in today's touch interfaces. However, Dual suffers from two limitations, which are limited modes available and the lower efficiency, say 1 second per switch. As such, many researchers have been explored to increase the touch input vocabulary. For example, single tap mode switching, which improves the time efficiency by differentiating different types of touch, such as using different parts of the finger, different contact areas, or different level of forces. And another category is the two-step mode switching, which determines a mode according to the touch motion that came after the touch, such as rolling, shearing forces, and the in-air motions. And although these novel approaches can potentially enable many modes, they have two limitations too. First, they often require extra motions and require users to learn and memorize the motions in association with the modes. And second, most of them require additional sensors beyond the touch screens. We therefore propose DualPlus. Like typical Dual Touch, DualPlus requires at least the motor space and no additional hardware. And more importantly, it allows for multi-level fast selections. We enable this by augmenting touch with rapid haptic ticks. With these ticks indicate the switch of modes, enabling users to accurately access a mode using single touch of various dwelling time. So up to this point, I have introduced the background of DualPlus, and let's talk about the design, the research questions behind the effective DualPlus design. So the first question came to us was the effective level of DualPlus. In general, the accuracy degrades when counting more vibrations for greater values. For example, counting vibrations, first or second vibrations is easier than counting 8 or 9 vibrations. Therefore, the question is, when does the accuracy start to degrade? Secondly, if the degradation is inevitable, then can we extend the effective levels? Moreover, the Drill Plus use haptic counts to notify the mode switch, but many touch interfaces do not have built-in haptic functions, such as the traditional keyboards, the touchpads, and the buttons found in our daily life. Those devices do not give us the active vibrations. Other examples are the on-body interfaces that it is still challenging to deploy haptic functions on touch interface on skin or clothings. For that, our third question is how to enable the Drill Plus functions on those non-haptic touch interfaces. So with a series of user studies, we try to answer these three questions, and the result leads to the optimal Drill Plus haptic design. The goal of the study one is to find out the effective level of monotonous Drill Plus. In the pilot study, we determined 4 candidate intervals as the independent variable of these studies, which are the 170 milliseconds, 150, 130, and 110 milliseconds intervals divided by short 10 millisecond haptic ticks. So for all intervals, we ask the participants to select a target vibrations using one of the 2 gestures, the single-handed thumb input on the left and the two-handed index finger input on the right. And the target vibration in each trial was set to lie between 0 to 9. 0 refers to simple touch, and the 9 means that the user have to count vibration up to 9 and release their fingers to select. So after the participants collected the top ticks with a drill touch, he lifts the finger and the actual solution will be displayed on the screen. This study was between subject design with 4 intervals at participants, 2 gestures, and 200 trials for each gestures, which makes totally the 12,800 data points. As we expected, the accuracy drops significantly as the target value grows higher. In general, the accuracy of selecting vibration 0 to 3 are higher than selecting vibration 4 to 9. That means the effective level of a monotonous Drill Plus is less than 3 vibrations. There are some more details about this analysis. If you are interested in that, you can refer to our papers. So we proceed to the second study, which tackled the next questions, how to extend the effective level for higher level selections using Drill Plus. Let's look again at the basic design of Drill Plus. Each vibration is identical. So it is monotonous, it is boring, there is no reason in it. So we argue that adding reasons would help users to count bits. So we add reason to the vibrating ticks, and we call it the trunk design. By arranging multiple bits into groups, we can count them more stably as we enjoy the music. So then a follow-up question is how to trunk properly. Fortunately, the result of the previous study already provided a clue that for most cases, the effective level is 3 vibrations. So we therefore propose 3 bits per trunk design and believe this could enhance the stability of counting ticks. And we call it trunking Drill Plus design. And we try to make our trunking design simple and easy. Hence, we implement it by simply extending the first vibration of every 3 vibrations, which makes a 3 bits reason to the receivers. So it's like a beep, 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 beep as the vibrations. And this trunking design is tested in our study 2. Again, the 2 common gestures were included. On the left is the single-handed thumb input, and on the right is two-handed index finger input. The procedure and task were same as the study 1, and the participants were asked to perform a selection of a given target value in each trial. The only difference is that in these studies, all participants were applied with, in this study, all intervals were applied with 3 bits per chunk reason. Before the study starts, all participants were informed about that this reason will be presenting in haptic ticks. Again, the study was between subject design with 12,800 data points, and this is the result of the study 2. Comparing that to the result of original monotonous haptic ticks, it is clear to see that the performance of higher level selection was improved. Take a closer look at the 2 slower reasons, the 170 millisecond interval and the 150 millisecond intervals, and we can find relatively stable and effective performance. For the 171, the slower trunking design, the overall performance is around 95% accuracy across 10 level selections. And for the 151, the faster trunking design, and we can still achieve 94 accuracy for the first 5 selections. At this point, we found two optimal designs for dual pass selections, which are the 171, that is slower but allows for higher level selections up to 10 levels, and the 151 that is potentially more stable for quick and short selection within 5 levels. So in the final studies, we want to answer the last questions, how to generalize dual pass to the non-haptic touch interfaces. And the answer is, the vibration ticks are not necessarily come from the touch interface itself. We could separate the vibrations and touch. So therefore, the user performs the touch with their one hand, and the vibration ticks can be delivered to the other part of their body, such as the wrist from the smartwatch. So the other example include that the user performs the touch interactions through the stylus on the right hand, and while the left hand touching the tablet, which delivers the vibrations. To investigate the accuracy of such disparate touch vibration situations, we conducted study 3. The study design is very similar to the previous studies. However, this time, the participants touch a separate copper foils with their right hand to activate dual pass, while perceiving the vibration cues from the other hand holding the phone. And the result shows that whether the touch input and the vibration output are co-located or not, there is no difference in accuracy using 170 millisecond trunking design. And also there is no difference using the 150 millisecond trunking designs. So the study results suggest that we can use a vibration output to provide haptic cues to these non-haptic touch interfaces. After the 3 studies, we want to conclude the most important things for you here. First, monotonous vibration suffers from the degradation in performance in higher level selections, but these degradations can be improved by 3 bits per chunk design. Second, to enable effective dual pass, the touch and the vibration are not necessary to be co-located, which allows the dual pass to be applied to non-haptic touch interface for wider applications. And we categorize our application into 2 parts. The first part is the dual pass on vibration-capable touchscreens, the application including here what we have shown before. That are smartwatch, typing on smartwatch and smartphone, and also secret input and augmented stylus-based interactions. Also, on the non-haptic touch interface, dual pass can be used for enabling fast mode switching on keyboards. Notice that the vibration ticks here is come from the smartwatch, not from the touch interface itself. So including also augmenting functions with single button devices and small touchpads, such as the touchpad in the Google Glass. So there are many things to be discussed. Here I only discuss several key issues. Dual pass, first, exclusively works on haptic channel in this work. It becomes a limitation that users need to memorize the functions of the mode by heart. One potential solution is to have DualPrus also work with visual and audio cues. However, one should be aware of that these two channels might be competing with each other, and the visual cue might override haptic cues and vice versa. So whether mixing these two channels is a good choice or just a distraction needs further studies. And the second issue is applying DualPrus across different body parts. Through the smart rings, smartwatch, or smart belt, the vibration can be delivered to these different body parts. But this effective DualPrus design on these different body parts also need further studies. Finally, DualPrus can be easily integrated with other input methods, such as using different orientational finger plus DualPrus, or different gestures. Finally, I would like to summarize our work. In this paper, we introduce the concept of DualPrus, which enhance human perceptions of time using haptic tics. We conducted a series of user studies to obtain the design guideline and optimal reasons, which are the two levels with 3-bit per trunk design that provide about 95% accuracy for 5 and 10 level selections respectively. And we also present a wide range of applications by enabling DualPrus to work with non-haptic touch interface by separating the vibration output from the touch input. And I would like to also acknowledge our other authors, the Liao, Yen-Chiu, Chen, and the Chen. With that, I'm happy to take questions. Thank you.
All right, we're going to have time for a single question. Anyone? The microphone's right there. I have. Oh, okay.
Hi, Andy Wilson, Microsoft. One of the problems with pressure-sensitive touchscreens is that it's difficult to find different levels. You know, it feels like a very continuous domain. And it strikes me that one of the things that you have here is a means to